Okay, so we are hello. Yeah, so we are back. The power failure was there, so that's why we have hello. Yeah, so we are back. The power failure was there, so that's why we have um, yeah. So because of power failure, we have got disconnected. So now we are back. So yeah, so we were discussing about this aldol condensation, right? And we have because of power failure, we have got disconnected. So now we are back. So yeah, so we were discussing about this aldol condensation, right? And we have now we are back. So yeah, so we were discussing about this aldol condensation. Okay, so we have done this four different products we get depending on this cross condensation and self condensation reaction, and all these four products that we have A, B, C, and D. Okay, the composition of the product is it is maximum for A, then C, then B, and then D. Why D is minimum? Because both carbon ion source are ketones. Like both compounds are ketone only in this, and we know the ketones are less reactive. Okay, than aldehyde. That's why the composition of these minimum over here. Okay. Now you see here the alpha hydrogen of aldehyde takes part in the reaction, and here the alpha hydrogen of again aldehyde takes part in the reaction. So here we have aldehyde, here we have one ketone, which is again less reactive. So obviously A will have maximum, okay, and then we have C, and then we have B, and then we have D, right? So this is the order we have of the product. Okay, so if you take this acetone and acetaldehyde, depending on the mechanism, whether it is cross condensation or self condensation, we'll get the product. Okay, but now the important thing here it is what that how many different products we get. Okay, so you see because of cross condensation we are getting two products here, right? Because of this cross condensation we are getting two products here, and self condensation we are again getting two products here. Okay, so both that, so the total number of product, if somebody asks, then the answer will be what? 2 plus 2, 4. Total 4 products we get into this. But again, in the question, if they did not mention about this number of products and all, what will be the product in this reaction, then our answer will be what? Our answer will be first, because it is the major product we have in this. Okay, so these are the some like basic reaction we have, important reaction we have of this for aldol condensation reaction. Now the next thing that is important in this chapter, and that we are going to discuss here, and that is Cannizzaro reaction. Okay, Cannizzaro reaction. In this also we take two molecules of it. Okay, we'll discuss this Cannizzaro reaction first, then we'll see some questions which has been asked in JE exam. Okay, so the next reaction we are going to discuss is Cannizzaro reaction. Okay, see Cannizzaro reaction, in this also we take again two molecules of aldehyde. Okay, two molecules of aldehyde. So in this we write two molecules of aldehyde, and this without having alpha hydrogen, without alpha hydrogen. Two molecules of aldehyde without having alpha hydrogen undergo disproportionation reaction, disproportionation reaction, which we also call redox reaction, in presence of a strong base. in presence of a strong base. Okay, and in this the product will be what? The product will be an alcohol or salt of an acid. Okay, the product will be an alcohol or the salt of an acid. Suppose the first example, if I write here, suppose I'm taking this HCHO plus HCHO, two molecules of this, no alpha hydrogen. Okay, and the reagent we are using here, suppose NaOH, base we have NaOH, one molecule get oxidized, and that will be HCOO Na, salt of this acid will get, and other one will give you alcohol, that is CH3OH. Okay, CH3OH. Now if I take the another example, suppose we have PHCHO, benzaldehyde, plus again PHCHO NaOH. The product here, it is what? We'll get PH CH2OH plus PH COONA. Like this, one molecule is getting oxidized and other one is getting reduced. Okay, this is how this goes. Now here you see the important here thing is the product you can write down easily. Okay, one, it is oxidation and reduction. Remember one thing, that we are not getting here this acid, we are getting salt of it. Okay, and if you remember one more thing that I have told you in this carboxylic acid chapter, that in basic medium, if you do the hydrolysis of esters, that also won't give you acid, it gives you salt of acid. Okay, so that's the same thing. You can relate this and you can memorize this. Okay, now you see, if I talk about the mechanism, we can discuss the mechanism in two different way in this. We can discuss the mechanism in two different way, and that is what? Suppose we have HCHO first, C double bond O, H and H, HCHO. Okay, now in basic medium, OH minus. Okay, basic medium, OH minus. So we know this carbon is what? This carbon is having some positive charge because of polarity of this bond. This pi bond goes here, so we'll get what? OH CH H O minus. We get what? OH CH H O minus. Right, now the another molecule that you have, let me write down the another molecule like this here. Okay, now in this what happens, one of this hydrogen, one of this hydride ion, this or this, any one of this hydrogen goes onto this carbon atom when this negative charge comes over here. So this negative charge comes over here, and this hydrogen shifted onto this carbon atom, and at the same time this pi electron goes here. Okay, so we get here what? Negative charge comes over here. So this negative charge comes over here, and this hydrogen shifted onto this carbon atom, and at the same. So we get what? H. So we get what? H. Sorry, OH we should write. We get this. This is what? C double bond O H OH. So H O C H double bond O, plus we get what? H C H H and O minus here. Okay, now in this again proton exchange takes place and we'll get OH over there. Okay, proton exchange takes place into this, and we get OH. So what happens in this? You see this hydrogen atom, which is attached with the oxygen. This comes onto this oxygen atom. And it forms CH3OH and HCO minus. Okay, when proton exchange takes place from this proton exchange, so it forms O negative, C double bond O, H plus HC, HOH. Okay, so this is what the product we have, and since we are using this OH minus here, so Na plus we already have. So with this Na plus, it forms the salt of it. Okay, HCOO Na. Okay, so this is how we write down the product or the mechanism of Cannizzaro reaction. Now the important point, 2 3 points here for JE point of view, you must write down since you have done a bit of kinetics also. So rate law expression, if you write down, so rate law expression for this will be R is equals to the concentration K and the concentration of the aldehyde HCHO plus into the concentration of the base also will write down. Okay, concentration of the base also, right? So if you see, so it is a bimolecular reaction. Okay, it is a bimolecular reaction, and final concentration, oh, I forgot to write down 2 over here, right? This is the rate law expression we have for this reaction. Okay, so this is 2 molecules we have into this, so this is bimolecular. Okay, order of the reaction is 3. So order of the reaction is 3, bimolecular. With respect to aldehyde, you see the order is 2, and with respect to the base, the order is 1. Okay. Okay. Now, very like for the advanced point of view, for JE Advanced, one more thing we'll discuss over here. You see, just keep this in mind because I'm going to rub this off. Okay. It is a bimolecular reaction, order is 3. Okay. There is one more mechanism possible over here. Like what I have done here, when this when this bond pair comes over here, this hydrogen goes here, right? One possibility is what? One possibility is what? That this hydrogen, the transfer of this hydrogen may also takes place from the base. And what is the base? This is the base we are having. You see here, the base is this, and the same OH we have here. So another mechanism is what? In which this hydrogen also get transferred. Okay, that is also possible. So when this H plus comes out, okay, when this H plus comes out, so this also forms here O minus, and then this H gone over there, right? So when, and this kind of mechanism is possible. That mechanism is not that important. Okay, so I'm not going to draw the whole mechanism again, but what I'm telling you, that this hydride transfer that you have, H minus H plus may come out from this OH group also, right? H minus may come out from this OH group also. Now when this the condition is what for this? The condition is the concentration of base is high. Okay, so if the concentration of base is high, then what happens? That is what we are going to see. Okay, this the first reaction that we have done. It is possible when the concentration of base is 50%. 50% NaOH if you write, then the mechanism is that we have done just now. Okay, but if the concentration of the base is high, if the base has high concentration, high concentration, remember this kind of question they haven't asked. Okay, but maybe or may not be, because you should know this thing just over here, that if the concentration of base is high, then the rate expression that we write here, that the rate expression will be R is equals to, rate expression will be R is equals to K concentration of HCHO square and the concentration of base to the power 2 again. Okay, so with respect to the aldehyde and base, the order of the reaction is 2. Overall order is equals to 4. This is a fourth order reaction, bimolecular reaction. Okay, second order with respect to aldehyde and second order with respect to the base. The overall order is fourth order reaction, and the um, and the molecularity is 2, biomolecular reaction. Okay, so this overall order will be 4 here. In previous case it was 3. Okay, so this is only possible when the base concentration is high. And how it is takes place, that the transfer of hydride ion from the base also it is possible, OH group also it is possible. Okay, and when it is possible, when the concentration of base is very high. So when the concent that's one thing to sum up all this discussion. If the concentration of base is very high, okay, then the hydride ion transfer takes place from the base, and in that case the order of the reaction will be 4. Okay, and that will be a complex reaction. Okay, it is not easy reactions. Fourth order reactions are very complex, so it is a complex reaction. Okay, now we'll come to this part, Cannizzaro reaction. We'll come to this again. There is one more reaction we'll discuss into this. But first of all, since we have discussed already that what is aldol condensation, what is Cannizzaro reactions, so let's discuss all these things in the form of a question. That what kind of questions they have been asked in the exam. Okay, so if I give you the first question into this, which was asked in JE exam. Okay, the first question is this, that base catalyzed aldol condensation occurs with. Okay, base catalyzed. The question is this: base catalyzed aldol condensation occurs with. The options are, just to write down this small question we have: propanol, benzaldehyde, benzaldehyde, 2-methyl propanol, 2-methyl propanol, and the fourth one is 2,2 dimethyl propanol. Okay, so I'll give you 1 minute. Okay, base catalyzed aldol condensation, you have to tell me the answer. Which of these compounds shows base catalyzed aldol condensation? 1 minute I'll give you. Just you draw the structure of this, check whether we have the alpha hydrogen present or not, because for aldehyde, for aldol condensation we need alpha hydrogen. Okay, just you tell me which one will have alpha hydrogen present, and then you tell me the answer. This is a multiple choice question. It is a multiple choice question. Okay. The answer of Nikhil is telling me the option A is the answer. Okay, so the first answer, first response I got is option A. First option I got is option A. Okay, so what we have to check into this, that the presence of alpha hydrogen, right? So if I draw the structure of propanol, first of all, let me draw the structure of all this. Propanol is what? CH3, CH2, CHO. It is propanol. Okay. Benzaldehyde is what? This is option A. Benzaldehyde is what? We have phenyl group and then CHO. Third option is 2-methyl propanol. So we have CH3, CH, CH3, and then CHO. And option D is what? 2,2-dimethyl propanol. So it is CH3, CCH3, CH3, CH3, and CHO. Okay. So now in this we have to check which one shows this aldol condensation. Okay, so for aldol condensation alpha hydrogen is required. Okay, so we have in the first option, obviously we have alpha hydrogen present over here, right? Alpha position. So this is obviously true, and as I said that the question is multiple choice. Benzaldehyde, we don't have any alpha hydrogen present here, not possible. In this we have alpha hydrogen present, in this we do not have alpha hydrogen present. So B and D is obviously not true into this. Okay, so if you see this one has alpha hydrogen present. Okay, but then also this compound will not show aldol condensation reaction. Why it does not show? Because in this condensation is not possible, only we have one hydrogen present into this. Okay, since only one hydrogen is present, so condensation is not possible. It shows aldol addition reaction. Okay, so for condensation we must have more than one, at least two alpha hydrogen we must require over here, right? So basically this compound does not show aldol condensation. This forms aldol. Okay, this forms aldol addition reaction. That is what aldol addition reaction. So this is not true, these two are not true, so answer is option A, which has given by Nikhil. Okay, so this was the correct answer. Anyways, so this question was asked in JE exam. Okay, and if you see the JE exam, it was asked in like the long back. But again, it is important. Usually, students check alpha hydrogen and then it gives the answer of this one also, right? You must take care of this thing that 2-methyl propanol does not show aldol condensation. Okay, because of this, and some in some books they have given the explanation also that this because of the plus I nature of these two, right? The removal of this H plus is difficult over here. Plus I. So H plus holds firmly over here with this carbon atom. That is also one of the reason. But anyways, this does not show. Okay, any one of the um, a reason you can or logic you can apply, you'll get the same answer. Okay. One more question you see the following compounds which reacts with ethanolic KCl. Okay, ethanolic KCl. This one you let it be. We'll give you some other question. Okay. Now you see one reaction here. One question. Again, one question that they have asked that which of these compounds goes under aldol condensation? Okay, which of these compound goes under aldol condensation? First one they have given acetaldehyde. Acetaldehyde is what? CH3, CHO. Alpha hydrogen possible. Yes, it goes under aldol condensation. Second one is what? Second one is propanaldehyde. Again, it is possible. Okay, possible. Third one is what? Third one is benzaldehyde, not possible because there is no alpha hydrogen present into this, not possible. Fourth one is what? Fourth one is tri. This one you tell me tri deutero benzaldehyde, trideteroacetaldehyde. Sorry, DEUTERO acetaldehyde. This is again a multiple choice, more than one answer we have into this. These two is true. This one is not possible, right? Trideteroacetaldehyde is this. Instead of hydrogen, we have three deuterium. Okay, CHO. So whenever you have D presence in presence of in place of hydrogen, we consider deuterium also follows the same pattern of reaction as hydrogen. Okay, so the answer is also fourth one also gives you the right one into this. Okay, now one question you see that is also a good question. Okay, that is all. This question was also asked in JE exam. Okay, so all the question that we are discussing today, they have asked in JE. So you try to understand how they frame the question in JE exam. Okay, you see the another one I'll give you. Like they have, what is the question? You just see first. A new carbon-carbon bond formation is possible. The question is a new carbon-carbon bond formation is possible in first option. Is possible in first option Cannizzaro reaction. Cannizzaro reaction. Second option Friedel-Crafts reaction. Friedel-Crafts reaction. Third option Clemmensen reduction. Clemmensen reduction. And the fourth option. And the fourth option, it is Reimer-Tiemann reaction. Reimer-Tiemann reaction. So the point is, in which of these reactions a new carbon-carbon bond forms? That is the question. Okay, so you see, for to answer this question, you should know all these four reaction actually. If you do not know the reaction, what is Cannizzaro, what is Friedel-Crafts, what is Clemmensen, what is Reimer-Tiemann, then you cannot do this particular question. Okay, so if you see the Cannizzaro reaction is what? It is a disproportionation reaction. Okay, so obviously in this there is no carbon-carbon bond forms. Okay, and just now we have discussed one molecule get oxidized and other one get reduced. So this one not possible. Cannizzaro reaction. Friedel-Crafts reaction, if you see, and if you remember what is Friedel-Crafts reaction, we have a benzene ring. I'll just write down here only. We have a benzene ring, and this benzene ring reacts with what? Reacts with CH3Cl, methyl chloride, in presence of anhydrous AlCl3. Anhydrous AlCl3. And the product, if you remember in this, will get toluene. Okay, if you have benzene ring and here we have CH3. So this you see one extra or new carbon-carbon bond forms over here. Right? So answer here will be Friedel-Crafts reaction. It is correct. We'll see whether another one is possible or not. Clemmensen reduction, if you remember, we use what is the reagent we use here? ZnHg, right? ZnHg with conc HCl. And if you remember this C double bond O, if you use ZnHg with concentrated HCl, this C double bond O converts into what? CH2. Right? So there is no new carbon-carbon bond formation into this. Okay, so this one is also not possible. Okay, Reimer-Tiemann reaction, it is a reaction of phenol. Okay, so if you see here, we have phenol OH, and this reacts with chloroform CHCl3 plus any base we use OH minus KOH OH minus we can use. Then we get into the product is salicylaldehyde into this CHO. You see, this is the carbon-carbon bond. We have new carbon-carbon bond. This is also our answer into it. Okay, so like this, they frame the question in JEE, which you have to keep in mind. Okay, now the another one you see. Okay, one more question you see. A mixture of benzaldehyde and formaldehyde on heating with aqueous NaOH solution. Okay, so the question here it is a mixture of benzaldehyde and formaldehyde on heating with aqueous NaOH. Benzaldehyde and formaldehyde on heating with aqueous NaOH solution. So benzaldehyde is this benzene with CHO. Formaldehyde is HCHO. NaOH, aqueous NaOH we are using and we are heating this. Okay. What kind of reaction is it? This is a Cannizzaro reaction. Right? There's no alpha hydrogen present and a base we have here, or Cannizzaro reaction. So when this reaction takes place, so it forms one will get oxidized and other one will get reduced. Okay, HCOONA plus CHO will get reduced and it forms CH2OH. The reduction of CHO gives you CH2OH. So this is what the product we get into this. But the option is written in something else like benzyl alcohol and sodium formate, sodium benzoate and methyl alcohol. Like this, they have framed the option, right? So this one is what? This one is benzyl alcohol and this one is sodium formate. Okay, so benzyl alcohol and sodium formates forms to this. One, you must keep in mind one thing, that Cannizzaro reaction we are using two different aldehyde into it. So this kind of cross Cannizzaro reaction. Cross Cannizzaro, when two different aldehydes are there. Cross Cannizzaro reaction. Okay, and when one of the aldehyde is formaldehyde, then this always goes under oxidation. Under oxidation. Formaldehyde always undergo oxidation if it is present in the reaction. Okay, and we already know that oxidation of aldehyde gives you acid, but since it is a basic medium, so it won't form acid, but it forms salt of acid, and that's where we are getting HCOONA. This question was also asked in JEE exam. Okay, so you can see like how it is important, the Cannizzaro reaction and this aldol condensation. Okay, now we're moving forward into this. Now we're moving forward, and one very important reaction we have, which is based on this only, that is Claisen-Schmidt reaction. Okay, the one important reaction we'll discuss next, that is Claisen-Schmidt reaction. Okay, so next reaction we are going to discuss. Clemmensen reaction. Now, this reaction is what? Aldehyde which does not have alpha hydrogen in presence of a dilute base condense with aldehyde or ketone containing alpha hydrogen. Okay, so this in this I'll just write down all this thing in short. One aldehyde we are taking plus another one is aldehyde or ketone. Aldehyde or ketone, and it forms beta hydroxy carbonyl compound. It forms beta hydroxy carbonyl compound which goes under dehydration, which goes under dehydration to form alpha beta unsaturated carbonyl compound. Unsaturated carbonyl compound. Okay, so here you see this aldehyde which is reacting in this, okay, in presence of a dilute base we are using here, okay, like NaOH and all, dilute base. Alpha have aldehyde having no alpha hydrogen. Here we do not have alpha hydrogen, and when this is condensed with any aldehyde or ketone having alpha hydrogen, then this reaction takes place, right? It means one aldehyde does not have alpha hydrogen, other one have alpha hydrogen. So if I write down the example, see, we have benzaldehyde, pH CH double bond O, plus acetaldehyde, CH2 CHO, and one hydrogen here, right? So it is also the same kind of reaction we have. This alpha hydrogen comes over here, and this carbon and carbon joins, so it forms what? pH CH OH CH H CHO, and when you heat this dilute base we are using, dilute NaOH base we have, when you heat this H and OH comes out at H2O, and we'll get pH CH double bond CH CH O. This is what the product we get. Okay, now in this you see we are getting this double bond at alpha and beta position. Here we have alpha, here we have beta. Okay, so alpha beta position we have double bond here, so we call it as alpha beta unsaturated carbonyl compound. Alpha beta unsaturated carbonyl compound, and this we call it as Clemmensen reaction. This compound, the name of this compound is what? It is cinnamaldehyde. This one I have done in the class. The same reaction we call it as Clemmensen reaction. Okay. Now this reaction may also takes place with same aldehyde also, right? CH3CHO and CH3CHO. Okay. So when you take here CH3, right, then the reaction takes place in the same manner, but that is not Clemmensen reaction. Instead of this pH, we'll get CH3 here, and that compound we call it as crotonaldehyde. Okay, the name is not that important, so I'm not writing down that particular reaction. Okay. Now, This reaction, Claisen-Schmidt reaction, is same type of cross aldol condensation reaction. But in cross aldol condensation reaction, here you see this one is what? This one does not have alpha hydrogen. That's why sometimes in JE they have asked this question that which of these aldehyde does not show does not show aldol condensation reaction. Okay, so since we have benzaldehyde is this, benzaldehyde is this, right? PHCHO is nothing but this. This shows cross aldol condensation reaction with this, which we call it as Claisen-Schmidt reaction. So it is the same kind of reaction we have, that is cross aldol condensation reaction. Okay, now in this you see the one thing that like we should understand here, that is cross Cannizzaro reaction. Okay, in cross Cannizzaro reaction, like I said, that two aldehyde must have two different aldehyde we are using. Okay, two different aldehyde we are using, then only it is cross uh, aldol cross Cannizzaro reaction. Two different aldehyde having no alpha hydrogen. Okay, two different aldehyde having no alpha hydrogen. One thing, just we have just let me write down this thing that I have. If I write down the example that we have just now taken in the JE exam that they have come, PHCHO plus HCHO. Okay, this is important for this board also and JE mains also. NaOH we are using, and the product we write here what? This get oxidized whenever formaldehyde is there. Formaldehyde always get oxidized, so it forms HCONa plus PHCHO will reduce into CH2OH. So basically one is getting oxidized, other one is getting reduced. Okay, so now if I write down this compound, this is the reference we have taken to make you remind that how the reaction process cross Cannizzaro reaction. If I write down suppose this one, CHO here, and here we have methyl, right? And this reacts with one of the isomer of it, which is nothing but methyl here, and here we have CHO. It is cross Cannizzaro reaction, NaOH, dilute, dilute. It is cross Cannizzaro reaction. Okay. Now the question here it is what? Which one will oxidize and which one will reduce? That is the question. Otherwise, we know if this will get oxidized, it will be CONa here. If this will get reduced, CH2OH here. But whether this, how this methyl group that we are here, methyl group at ortho and para position, this is at para position and this is at ortho position. So how this methyl group will affect the formation of compounds here, that we have to understand. Okay, so let me write down the product first here. The product that we get into this, the product that we get into this is the product that we get into this is benzene, and then we have COO minus here. Here we have methyl plus benzene, methyl, CH2OH. CH2OH. Okay. Now you see, whatever product we are forming here, that product must be stable. Okay. So you can write down either this, because you know one will go under oxidation, other will go under reduction. You can write down either this or this. So if the another product, the answer is this one. Let me tell you, the answer is this. Okay. Suppose if you write down this one and we compare this next. Suppose if you write down this product also, COO minus, and here we have methyl, and here we have CH2OH. Oh, sorry, I've written the same thing. No? Let me erase it first. Okay, so the possibility is this COO minus, and here we have CH2OH. Okay, now the thing is what, either we have this as the product or this is the product. Okay, so coming back to this, you see now this methyl group has plus I nature, correct? Electron releasing nature it is. Okay, and this also has plus I group, electron releasing nature. Because of plus I nature of this negative charge is getting destabilized. Okay, the electron density on this oxygen is increasing, right? So this product is not stable. So obviously this product will not form, and hence this product will also not form. The correct answer will be this. Okay, so basic rule of that stability and all, how the plus I and minus I group or plus or minus R group affects the stability of any compound. On the basis of that, will form the product into this. On the basis of this only, one more example if you take, that is we have a benzene ring CHO. Here we have Cl plus benzene ring CHO. Here we have Cl. Dilute NaOH. Dilute NaOH. Okay, so the answer of this product will be what? Correct answer I'm writing down simply. This chlorine has minus I nature. That will be this. This ortho position chlorine will stabilize this negative charge here. So this will get oxidized. And this will get reduced CH2OH at meta position. This is the product we'll get. Due to the minus I nature of this negative charge is getting stable over here. Okay. Now, one more important example I'll just give you. Same concept is this. Suppose we have a ring CHO and we have OH present here. CHO and OH present at this position. Dilute NaOH. Okay, the product in this is what? COO minus, and this is the ortho plus CH2OH, and this is the para. This is the para. Okay, now why this? Now the reason here it is what? This OH group shows minus I and plus R both effect. Okay, because this oxygen has lone pair on it, and because of carbon oxygen electronegativity, carbon oxygen it shows minus I also, and plus R also it shows both effect. But the net effect is what? Net effect is electron donating. Plus R is dominate over here. Okay, so because of the dominating nature of plus R, the product is this. Okay, this and this. Like this, we can easily understand. And we also discuss this. How do we consider when we consider plus R or a minus I? That also we'll see when we do the carboxylic acid acidity of that. Okay, so this is what we have. The few example we have discussed. Okay, and this is it. We have some more reaction into this that we can uh, continue with in the another session. Okay, but today we have discussed Cannizzaro reaction. Okay, what all products we can get in Cannizzaro reaction, that also we have discussed. Okay, a few questions we have seen for JE point of view. Okay, what all question they may ask in Cannizzaro reaction, Aldol reaction. So okay, so the one question that I got from Purvik, that is there a way to determine the compound that get oxidized if the compound is not formaldehyde? Yes, we have a way to determine the compound which get oxidized. If you see the mechanism of Cannizzaro reaction, okay, then you will understand that there is a shifting of hydride ion. Okay, H minus ion is getting shift. Okay, so we'll discuss this thing. Chalo. Okay, so the compound which can easily donate the H minus ion, that will get oxidized. Okay, that's the simple reason we have. Okay, for why formaldehyde always get oxidized? Because this formaldehyde can easily donate H plus ion. Okay, if suppose any alkyl group is present on the carbonyl carbon, then alkyl group has plus I nature. Because of the plus I nature of alkyl group, the electron density on carbon atom increases. Okay, and removal of H minus will be difficult over there. I'll discuss one or two example onto this that you have asked, so I'll have to discuss this. Just give me 1 second. Okay, so you see, so like the logic we have for a compound to get oxidized is the tendency to donate hydride ion. Okay, the compound which can donate hydride ion will be easily oxidizable. Okay, so just logic you write down the compound. We are talking about cross Cannizzaro reaction, which are capable of donating hydride ion, donating H minus ion, are easily oxidizable. Are easily oxidizable. Okay, so what happens in this? So we determine by this by the charge density on the carbon atom. Okay, if carbon hydrogen bond form in which the H minus ion is coming out, the greater the negativity, the greater negative charge density on the carbon atom of CH group, greater the tendency for hydrogen ion to leave the carbon atom. So logic, the first compound or the first logic behind this is, suppose carbon hydrogen bond we have. Okay, carbon hydrogen bond we have, H minus has to come out, right? So if the electron density on this carbon atom increases, then it will facilitate the removal of H minus ion into this. Okay, now the first example of this, you see how the electron density on carbon increases, and that will facilitate the removal of H minus ion. And one thing you have to keep in mind, the compound which are capable of donating H minus ion are easily oxidizable. So you have to just check if you have two aldehyde or ketone. Aldehyde if you have in case of cross Cannizzaro reaction. The aldehyde, which can easily donate H minus ion, are oxidizable. That is what you have to keep in mind. Some examples we'll discuss over here. Okay. Now, if you have dianion present, okay, when there is di present, then it is easy for that carbon atom to donate hydrogen ion. Like suppose if I write down the example here, if I write down the example here, suppose one I am taking dianion. Okay, so R C H O minus O minus. One compound is this, and the another one is R C H O H and O minus. Okay, how do we get this and this? That you can understand from the mechanism of Cannizzaro reaction. Okay, this will get when we have the hydride ion H minus comes out from the base that we have just now discussed. We just now discussed that fourth order reaction and all. In that case, we'll get dianion if you see the mechanism. But all those things are not required, so I'm not giving you again those. If you have any this kind of dianion is present, okay, then removal of, if suppose one compound we have in which we have tendency to form dianion and another compound we have like this, then obviously the removal of this H minus is easier over here because of dianion present. So one condition is this: if dianion is present, then removal of hydride ion is easier into this. Okay, it's better hydride ion donor. So in this case, it is a better hydride ion donor. So one thing is this. The another thing is what? More electron donating. This thing you will not get mainly in the exam. One logic is this also. Well, now the important one is this into this. Okay, so let me tell you the second one, which is important for your exam point of view. Which one will donate hydride ion? Okay, if you have more electron donating group present, then the negative charge density on the carbon atom obviously will increase. How the negative charge density on this carbon will increase? If we have more electron donating group present. So because of electron donating group, right? Electron donating group, EDG. You see this example, if I have one benzene ring, right, and in this we have O minus, O minus, and H, right? And here suppose we have at this position we have OCH3 present. So CH3 we know it is methoxy group and it is electron donating group. So in this case, if you compare, and if you compare in this case, O minus, O minus, and H, these two compounds I am giving you. Suppose one more compound if I give you, O minus, OH, H, right? And last one is this. We have NO2 here. Okay. Now, if you compare the electron, the tendency to release hydride ion, since it is an electron donating group, we have electron releasing tendency to donate this hydrogen ion is maximum over here. So this has more tendency to donate hydride ion than this one, because in this we do not have any electron donating group present in the ring. Okay, both we have two dianion present. If this two, if you compare, so obviously this one will be more because everything is same. Here we have dianion with this logic, the first one. Here we have dianion, here we have one anion only. If you compare this one, so this is electron withdrawing group. So obviously this electron withdrawing group is less tendency to donate this hydrogen ion, because here the electron density is decreasing. Okay, so this is the last, the second one that I have given you. Two things you have to keep in mind, that the compound which can easily donate hydride ion are easily oxidizable. Okay, HCHO can donate hydrogen very easily. HCHO can donate hydrogen very easily. Okay, that's why it is always oxidizable. It is always get oxidized in this reaction. Okay, so two things you have to keep in mind: dianion and electron donating tendency. Okay, and how do we know that hydride ion donor are getting oxidized? That you will understand from the logic. You must keep in mind this H minus comes and then OH minus attacks onto this. Okay, so if you see the mechanism, you will understand this. Okay, so this is what you have to keep in mind. Okay, so next thing we are discussing about carboxylic acid. See, I'm telling you one thing: if you have to revise this particular chapter, you cannot leave this aldol condensation and Cannizzaro reaction, because these two are the most important reaction we have. Okay, and if they frame question, they'll frame from this aldehyde and ketone most of the time. Okay, whatever exam you are writing down, they'll frame from the this aldol condensation and Cannizzaro reaction. Any book if you pick up, you look at previous year question, 4 5 10 years question, you see from aldehyde ketone chapter, most of the question, 60-70% question you will get from this only, aldol condensation and Cannizzaro reaction. Okay, so next we see carboxylic acid. Little bit of that chapter also we'll discuss. We don't have that much time today. Okay, so now carboxylic acid are what? Carboxylic acid um, are generally various reaction of carboxylic acid. We have seen that takes place with the formation of nitrines as an intermediate. Okay, so those reactions, name reactions are there. We have already done those reactions. The important thing we'll discuss here, that is acidity of carboxylic acid. Okay, so any carboxylic acid are C double bond O, OH, is acidic in nature because it can lose H plus and form carboxylate ion. This is carboxylate ion. Okay, so if this carboxylate ion is stable, then acidity will increase. Okay, more stable carboxylate ion, more will be the acidity of carboxylic acid. Okay, so if you have any electron withdrawing group present, EWG, electron withdrawing group, stabilizes the carboxylate ion, carboxylate ion, and hence increases the acidity of carboxylic acid. Acidity of carboxylic acid. Okay, electron releasing group, just reverse of this. Any electron releasing group, if you have, the negative charge density increases, stability decreases, and hence acidity decreases. Okay, acidity decreases. Now the important logic into this we have to understand, that is ortho effect. Okay, ortho effect we'll discuss here. We'll see some examples first. If you see the structure or resonating structure, one important comparison I'll give you first. If you compare formic acid, okay, H C double bond O, OH, formic acid, and benzoic acid. So benzoic acid is this. If I ask you which one is more acidic, what is the answer of this? Anyone? Which is more acidic? Formic acid and benzoic acid. Which one is more acidic in this? See, we can understand this to comparison. Obviously, this formic acid is more acidic than benzoic acid. Okay, you see here, if I write down the conjugate base of this, that will be H C double bond O, O minus. And this one is what? This one is resonance stabilized. C O minus and double bond O. This is the resonating structure we have of this. Okay, this pi electron comes over here, negative charge, and pi electron goes here. Okay, so this is what, this is resonance stabilized. Okay, and this resonance we are call it as equal resonance. Equal contributors, these are equal resonance. If you draw the resonating structure of this, okay, that will be, let me draw like this. C double bond O, O minus, and resonating structure of this is this pi electron comes over here and this goes here. So we can write down the resonating structure as positive charge here, double bond C, O minus and O minus. Okay, C, O minus and O minus. Okay, so here you see the negative charge on this is on the oxygen atom, and here we have positive charge. But positive charge in the ring, we can draw the another resonating structure also, and then the next resonating structure also. So the positive charge here will be at the alternate carbon atom. Okay, so that will be what? Alternate carbon atom. So uh, that will be the resonating structure, but that is not the equal resonance over here. These are the resonating structure, but not equal resonance. Equal resonance. So if you talk about the stability of these ions, the stability of this ion is more than all these ions that you have. Okay, and that's why the formic acid is more stable than what? Than the than benzoic acid. Sorry, formic acid is more acidic than the benzoic acid. Okay, if you see the Ka value of benzoic acid, it is 6.3 into 10 to the power minus 5. It is 1.7 into 10 to the power minus 4. You see, the Ka value of formic acid is more than the Ka value of benzoic acid, and that's why it is also more stable. See, whenever we have this kind of organic compound, most of the time we can explain the acidity and basicity order on the basis of uh, various electronic effects that we have, aldehyde, ketone, and all. Okay, but sometimes when we have more than one kind of electronic effect is taking place, then it is very difficult to explain the overall nature of the product. Okay, then it is mainly explained by the Ka value of the compounds. Okay, so if Ka value is more, then it is more acidic. Okay, and then first we find out the Ka value, and then we try to explain the logic behind that acidic order in the best possible way. Okay, so like somebody already asked me all these things, that in this benzoic acid we can draw 3 4 5 resonating structure, but here we have only two, and we also know more resonating structure means more stability. Then why not this one is more stable than this, and why not this benzoic acid is a better acid than formic acid? Okay, that is a genuine question. But the thing here it is what, that here the negative charge is equally distributed over the entire molecule, right? So this is the equal resonance condition we have, and with when equal resonance is there, then we do not consider the number of resonating structure. We'll see whenever it is equal resonance is there, it is always more stable, and that is also have the, you know, have, and that logic is also true when we see the Ka value of the compounds. Okay, so that is why this formic acid is more acidic than benzoic acid. One important comparison it is, so you must keep in mind. Okay, now the important, one more important thing that you have to discuss here before going into the aromatic acid comparison. Okay, and that is ortho effect. Ortho effect. Ortho effect, we also call it as SIR effect. SIR effect is nothing but steric inhibition, steric inhibition of resonance. Steric inhibition of resonance. Okay, so what happens in this, you see, whenever you have any group present at ortho position, any group present at ortho position, and here we have COH double bond O, COH double bond O. Okay, so this compound, if group is not present at ortho position, this compound is what? All carbon atom. If you see this benzoic acid, simple benzoic acid, COOH, all carbon atom are sp2 hybridized, so it is a planar molecule, right? It is a coplanar molecule. All uh, atoms are in the same plane, and since it is planar, so resonance is possible, right? Now if you have any ortho group at any group present at the ortho position, okay, so because of this group present at the ortho position, so we have some repulsion in this group, right? That is crowding, because of steric crowding. And when the repulsion takes place, this molecule, this group, change its plane to minimize the repulsion and gain stability, right? This group changes its plane, and hence now the molecule becomes non-planar, right? So the molecule becomes non-planar, and hence the stability or the resonance is now inhibited, right? Because we know resonance is only possible in planar molecule. The molecule must be planar. The p orbital must be parallel to each other. Then only the transfer of electron from one p orbital to another p orbital takes place, right? So if it is planar, resonance is possible. But when the group is present at ortho position, because of the repulsion or size of the group and carboxylic group, the carboxylic group changes its position, and hence the resonance is not possible now, because the molecule is not planar so far. Okay, not planar now. So this effect we call it as ortho effect, right? And since resonance is not possible now, so we are calling it as steric inhibition of resonance. Okay, so whenever we have any group present at ortho position, steric inhibition of resonance takes place, and this increases the acidity of compound, increases the acidity of compound. Okay, how it increases the acidity of compound? As we have drawn the resonating structure of this, just now we have drawn one structure. You see in this group C double bond O and OH, it withdraws electron, right? Because of this positive nature of this carbon and this electronegative difference. This pi electron comes over here and this pi electron goes here. Like this, we draw the resonating structure. So, and this is nothing but the resonance. So, when the resonance is not possible, it cannot withdraw electron from the ring, and hence the positive charge density on the carbon atom is more now. When resonance is not there, because of steric inhibition of resonance, what happens? The positive charge density on carbon, and this carbon of COH group, okay, on carbon does not decrease, hence removal of H plus is easier. If you have doubt, you can text me. And removal of H plus is easier. Okay, so now the thing here, it is what you understand my point. When resonance is possible, it withdraws electron. When it withdraws electron, the electron density here increases. When electron density increases in this group, removal of H plus is difficult, and hence acidity decreases. So because of resonance, what happens? This, when inhibition of resonance is there because of ortho effect, this group comes out of the plane. Resonance is not possible. The positive charge density on the carbon atom is now more in comparison to the other situation. So when the positive charge density on the carbon is more, it takes this electron pair towards its side, and which makes the removal of H plus easier. Okay, so basically in one simple line, whenever you have ortho substituted benzoic acid, then it is always more acidic than the meta or para substituted. Okay, so just this very important point we have into this, that you write down, note, ortho substituted benzoic acid is always more acidic than ortho sorry than para or meta substituted. We'll see the example, then you will understand. But this you must have to keep in mind. The reason behind this is what? The reason is steric inhibition of resonance, which we also call it as ortho effect. Okay, so now you see, if I take one example, all of you write down this: ortho substituted benzoic acid is more acidic than para or meta substituted. So first example we are going to see. This is very important as far as JEE or board is concerned. You will have these kind of questions in board exam also, like compare the acidic strength of this. So first one, we have COOH methyl COOH, CH3, ethyl COOH, and then we have COOH methyl. First one is this. Second question. COOH, CH3, CH3, COOH, CH3, COOH, methyl, methyl, and methyl. Third one, COOH, OH, OH. Okay. Now, if we compare all these compounds, first of all, in the first one, this is what we have: ortho effect, ortho position. Obviously, this one is most acidic, maximum. Okay. And CS3 has what? Plus I nature. CS3 has plus I nature. Okay. And because of plus I, acidity decreases, inversely proportional, right? So these two will decrease the acidity of benzoic acid. So this two obviously less than this. Okay. And here what happens? The plus I nature of CS3 is more over here than here, right? But in the fourth one, you see we have hyperconjugation effect also, right? Hyperconjugation effect is also there. So because of hyperconjugation effect, because the plus, if you imagine, if the plus I nature of this is more, right? So the acidity of this should be less than this if we consider the plus I nature, right? And here we have plus I possible, and along with plus I we have hyperconjugation also there, right? Hyperconjugation also there. So because of hyperconjugation, the acidity of this compound decreases, and because of plus I nature, right? So if you see the combined effect of plus I and hyperconjugation, The order is found to be this. So basically, 2 points you have to keep in mind. At para position, hyperconjugation also takes place. Okay, I effect is there. I effect is also here. And here I effect is more, right? So if I effect of this group is more over here, so ideally the acidity of this compound should be less than this, right? But what happens because of hyperconjugation, the acidity of this further decreases, right? And that you must have done in GOC, General Organic Chemistry chapter. Okay, so this uh, hyperconjugation and plus I effect, net because of net effect, the acidity of this is found to be less than this. Okay, more alpha, and we know because of hyperconjugation, acidity decreases. That you must keep in mind. Okay, so the net order of this is this only. Now the second question, you see, second question here, obviously we have ortho effect, right? In these two, if you compare, which one will have more ortho effect? Obviously this, because here we have larger group, repulsion will be more steric hindrance, right? And here we have both sides steric hindrance present. So here we have maximum ortho effect. First one is this, then this, and then the third one is this. Okay, now the last one, you see. Okay, in this one, the first compound we have, where we have hydrogen bonding also possible. If this group releases H plus from this, then we can have hydrogen bonding possible here, and we can have hydrogen bonding possible with this also. So in this we have two hydrogen bonding possible. Ortho effect is there, but hydrogen bonding is also there, and because of hydrogen bonding, the anion is getting stable. So here we have two hydrogen bonding, here we have one hydrogen bonding. Okay, so obviously the stability of this is more than this. Okay, now the last three, if you compare, okay, last three, the OH group at meta position, it won't show resonance effect, but it shows I effect, and that too minus I, because oxygen here is more electronegative than carbon. Here this oxygen does not show minus I, but it shows what? Plus I, sorry, plus R. Minus I also it shows, but that effect is less because it is far from this group, right? Plus its plus R nature is dominant. Okay, so because of plus R, acidity decreases. So this one obviously less acidic than benzoic acid itself. Okay, because of minus I, acidity increases. This one is more acidic than benzoic acid. These are the simple comparison we have, plus R, minus I, and all, right? But if you compare these two, here we have ortho effect, and hydrogen bonding. Two hydrogen bonding here, so most stable, most acidic. The order is this. Okay, so like this, we can compare the acidic nature of carboxylic acid. Okay, two more very important comparisons. So basically, to sum up all this, here you see one thing: because of electronegativity difference, it has tendency to withdraw electron. But this is minus I effect. But this minus I effect won't affect the acidity of this much because it is far from this. We see the third carbon, right? So minus I is not dominant over here. But since oxygen has sorry, lone pair on it also, so this can donate electron to the ring, and because of this plus R nature, the acidity of this acid decreases. Okay, two very important comparison, or like acidic order we have, that you write down the last two in this. If you have COOH here and chlorine present at ortho position, COOH, and this chlorine present at meta position, COOH, and chlorine present at para position COOH. Okay, let me write down this again. Chlorine here, COOH here. And one more comparison will do. These one. Now, can you tell me the acidic order of these? Okay. The first one is easy because you see in the first one, this chlorine shows minus I, minus I, minus I. Okay, all these groups shows minus I effect. Can it show plus R also? This you see, it has lone pair on this also. Lone pair here also we have. Lone pair here also we have, and here also we have. Okay, you see minus I lone pair is what? It is plus R is what? Donating the tendency to donate this lone pair of electron to this ring. So because of this plus R, acidity decreases, and minus I, acidity increases, directly proportional. So now what factor you have to consider over here, because both are opposing to each other, right? Both are opposing factor. Okay, so here you see, if you consider plus R effect, that is resonance, right? Resonance means what? Transfer of electron from one to another orbital. This carbon, you see, the carbon with which the chlorine is attached, this carbon is this carbon over here, this chlorine, right? So this chlorine has 3p orbital, and this carbon has 2p orbital. So since we have 3p and 2p, two different orbital we have, right? 3p orbital is bigger in size than 2p orbital. Two different orbital we have. So in this case, the transfer of electron from chlorine to the 2p orbital of carbon is not possible. Okay, so basically because of this, what we can say, that this R plus R effect is not possible in all these examples. Okay, plus R effect is not possible. So we'll consider only minus I in this. Okay, since we have 2p 3p orbital. So we'll consider only minus I and minus I. So minus I we have maximum in this because it is closest to this COH group. So it is the most acidic compound. Then we have meta, and then we have para, and last one we have this. So effect of minus I follows this order. Maximum at ortho, then we have at meta, then we have at para, because we are going away from the functional group. Okay, I hope it is clear. Now you come back when you see this compound. Okay, in this also we have same thing, right? Because this chlorine has all these halogen atom has lone pair on it. So again we can talk about resonance over here. Lone pair, lone pair. Here also we have three lone pair. Okay. Now as I said that this carbon is 2p and this chlorine is 3p, then bromine has 4p, iodine has 5p, but fluorine has 2p orbital. Okay. So with the same logic, if we try to conclude this, okay, so we get what? Here we have, because of this group, we have only minus I effect. Because of this group, we have only minus I effect. Because of this group, we have only minus I effect. But because of this group, we have minus I and plus R. In this, resonance is also possible. Minus I and plus R. And you see, this minus I and plus R are what? Opposing factor. They both are opposing to each other. Okay. All these minus I group, all these minus I group is increasing the acidity of benzoic acid. Okay. So we have five compounds. So obviously, since all these compounds shows minus I effect, so obviously this compound is the minimum acidic. The benzoic acid is what? The minimum acidic compound we have here, right? So this compound has fifth number, minimum acidic. Now fluorine, if you talk about the electronegativity of fluorine, it is the most electronegative element. Okay, so it has maximum tendency to withdraw electron. Okay, but at the same time, it has plus R nature also, and because of plus R nature, um, and because of plus R nature, the electronegativity decreases, right? So if we consider these two factors and if you draw the or write down the order of electronegativity, it is found to be maximum for chlorine, then fluorine, then bromine, and then iodine. Okay, this order we get when we consider the plus R effect of fluorine also. This plus R effect decreases the electronegativity of fluorine. Okay, and net effect is found to be in this order. Okay, so here the maximum acidic compound we have is because of the minus I nature of chlorine, and this compound is maximum. First one is this, second one is fluorine, third one is bromine, and fourth one is iodine. So order of acidity in this compound is chlorine maximum, fluorine, bromine, iodine, and then this benzoic acid. Okay, so this is how we decide the acidic nature of benzoic acid or any substituted benzoic acid. Okay, so this order you must remember. And when we have to think about plus R and minus R effect, plus R and minus I, that also we have discussed into this. Okay, plus R effect is only possible when we have same size of orbital, like 2p 2p, 3p 3p, like this. Okay, it is not possible in, it is not possible in 2p 3p orbital. It is not possible in 3p 4p orbital. You must have same orbital present over here, like we have here. Fluorine has 2p, carbon has 2p. So plus R also you have to consider. In all these, we are not considering plus R effect. Okay, so this you must keep in mind. Okay, now on the basis of this, if you consider some questions which has been asked asked over here. One question which has been asked in JE. This one you see. CN. Here we have NO2 and here we have OH. Here we have OH phenol and here we have COH. Now in this we are using 2 mole of NaNH2. 2 mole of NaNH2. Okay. The question is what? What will be the product here? Okay, they have given the option and I'm not drawing those compounds which is given in the option. This is the question. Basically, I'll tell you the question what it is. It is a base, right? Na plus NH2 minus. Okay. So NH2 minus we have base over here. Okay. This base will take the H plus from this compound. Okay. And since 2 mole we have, so we have 2 moles of this NH2. Okay. 2 moles of this NH2. So it takes what? It takes 2H plus. It takes 2H plus from the compound. And how many H plus it can give? It can give this H plus is the acidic hydrogen. This is the acidic hydrogen and this is the acidic hydrogen. So out of this three, only 2H plus can come out. Correct? So now that is what we have to find out, that which one, like what are those um, H plus we have which can come out in this reaction. Okay, so obviously the hydrogen which is more acidic, that will come out. So basically we have to compare the acidic nature of this group. We have one group is this, one group is this, and another group is this. You have to compare the acidic nature of this. Okay, sorry, here we have CH. Okay, so another group is this also, this also. So if you compare the acidic nature in all this, okay, if you compare the acidic nature, so if this is phenol and this is nitrophenol, okay, nitrophenol, nitrophenol has what? It is the minus I nature of NO2. NO2 shows what kind of group? It is minus I nature. This is the this group shows minus I, right? And we know carboxylic acid is obviously it is more acidic than the phenol. Okay, so if you compare this hydrogen and this, obviously one this H plus will obviously come out because of this is the most acidic group we have. If you compare these two, we have confusion in these two only, right? If you compare these two, right, then this is nitrophenol because of minus I nature of this one extra effect we have over here. The removal of this OH is easier. Okay, so the product here will write is this, which is given in the option. You can go through. Okay, but the product that they have written, and that will be like this. We have a benzene ring, OH as it is. Here we have CH. This benzene ring contain carboxylate ion here because H plus is taken up by the NH2 molecule here. Here we have benzene ring. This NO2 will be as it is, and here we have O minus. This is the product we get. So basically, it looks like a question based on chemical reaction, but it has nothing to do with chemical reaction. Okay, it is only based on what the acidity of this compounds. Okay, carboxylic acid is the most acidic compound we have here. So obviously, one H plus comes out from here. We'll get this. Okay, then these two, if you compare, because of minus I nature of this hydrogen is comparatively more acidic than this. So this will come out as H plus. So we'll get minus one, this minus charge onto this. So the product will be this, which is given in the option. Okay, so like this, we can compare the acidity nature and question based on this we can easily do. Okay, there are few reactions in carboxylic acid also we have, like we have in what all cases decarboxylation takes place. Okay, so decarboxylation is nothing but the removal of CO2. Okay, so removal of CO2 is possible and it gives you one anion over there. Decarboxylation, if you see, it gives you one anion over there. So basically decarboxylation will be easy when we have when the anion is stable. Okay, like you see, ease of decarboxylation, they have asked question onto this, ease of decarboxylation. Last thing we are discussing for today, that is ease of decarboxylation. Decarboxylation is nothing but it is the removal of CO2. Okay, and in this what happens when sodium salt of carboxylic acid, when sodium salt of carboxylic acid is heated with soda lime, then they form hydrocarbons by losing CO2. Okay, so in this the reaction we have, when the sodium salt of carboxylic acid is heated with soda lime. Soda lime means what? NaOH and CaO. 3:1 ratio. NaOH and CaO. Okay, carboxylic acid. Then hydrocarbon forms then hydrocarbon forms by removal of CO2. This CO2 comes out in the form of Na2CO3. It combines with there and it forms Na2CO3. So basically, if you see one reaction, C2H5 COONA heated with NaOH plus CaO, then it forms C2H6 plus CO2 plus Na2CO3. Okay, Na2CO3. So this what I say, the CO2 comes out in the form of sodium carbonate. Okay, Na2CO3. This is the product we get into this. Okay, now the question here it is, what if you have any compounds, okay, and if you have to compare in which compound the decarboxylation is easier, okay, for that the logic is same, right? And what is that logic? Because decarboxylation leads to the formation of an anion. Okay, so just let me write down this one. Decarboxylation leads to what's the formation of anion. Okay, if this anion is stable, like we have discussed for acid, conjugate base is stable, then acid will be um, acidity will be more. If anion is stable, then decarboxylation is easier. Carboxylation is easier. Decarboxylation is easier. Okay, so if you compare the decarboxylation of three compounds, like suppose if I can rub this off, okay, so we'll take one example to understand this. First one we have, that is Cl3 CCOOH. Okay, second one we have a benzene ring, methyl here, COOH. And the last one we have, third one, that is CH3 COOH. Okay, so here you see, if we try to write down the decarboxylation reaction of all these carboxylic acid, so first of all, we'll form the sodium salt of it, and that will be, if you put NaCl here, or suppose if it is given simply COO minus Na plus, this is the sodium salt of it. Here also, if I write down the sodium salt of it, methyl COO minus Na plus, or here if I write down the sodium salt of it, CS3 COO minus Na plus. Okay, now when this reacts with NaOH plus CaO, and when you heat this, it forms this anion Cl3C minus plus Na2CO3, which further by the addition of H plus forms Cl3CH, right? This also forms under the same reaction methyl benzene ring minus charge on it, okay, minus charge on it, which again forms toluene. This undergoes the same reaction and it forms CH3 minus, which gives you CH4 further. Okay, so now the question here it is what, that which one of these will go under decarboxylation reaction easily, and they have asked question onto this in JE exam. Okay, so decarboxylation will be easier when this anion is stable. Okay, if this anion is more stable, if this anion is more stable, then decarboxylation will be easier. So obviously, if you compare, we have minus I nature over here, minus I nature of this chlorine. Here we have what? Plus I nature of this methyl. Okay, so if you compare the stability of this anion, it is maximum for this one. Okay, this is for maximum for this. Then we have the second one, and in the last one, CS3 minus is least stable. Okay, so if you compare if the question is ease of decarboxylation, so this is most easily decarboxylated than this one and this one, because this anion is most stable than this one and then this anion. Okay, so like this we can compare the stability of or order of decarboxylation of any carboxylic acid. Okay, on the basis of this, if I can write down one last question for today, on the basis of this, that you see, you have to find out ease of decarboxylation. Last question for today, ease of decarboxylation. Okay, okay. The first compound, if I give you, which one will be easily decarboxylated? COH, right? And here we have NO2. Next one, COOH. Here we have NO2. Here we have NO2. And the last one is this COOH, NO2, NO2, and NO2. So decarboxylation reaction, if you see, like I told you, just you form the anion of it. Okay. So when you try to form the anion of this, you will get this benzene ring with negative charge here and NO2 here. Simply you remove that COOH and put negative charge over there. That will be the anion. Negative charge here. We have NO2 here and NO2 here. And here the negative charge will get here NO2, NO2, and NO2. Okay, and all these nitro group are electron withdrawing group. Okay, this is what EWG. This is also EWG. This is also EWG. And all these are EWG, electron withdrawing group. Okay, and if the number of electron withdrawing group increases, the stability of this negative charge increases on it. And when the stability is more, right, stability is this, and that is nothing but the order of decarboxylation. More stable anion, more easily decarboxylated. Okay, so this is it for today. Okay, so we are left with electrochemistry portion. Okay, that we'll discuss in the another session. Thank you.